This tutorial will demonstrate how to use the Gage Rating Curve Calibration Spreadsheet. This spreadsheet will be used to build a cross-section geometry shape while matching the user input gauge rating curve. The spreadsheet will use a gauge rating curve and cross-section assumptions such as bank fold top width, end values, and energy slope. The spreadsheet includes an instruction worksheet that will help guide you through the steps. Yellow cells are those that will need user input. Green, gray, and pink cells are those computed through formulas. Do not edit these. And blue cells are those that are computed through macros, however they can be adjusted. After identifying the gauge location, in this case I'm going to work along the Susquehanna River in Conklin, New York. We need to extract the rating curve information. You can do this by using the Download USGS Rating Curve Data tool found in the MMC Bathymetry toolbox. This can be from another source if available, as long as it's stage and discharge data. So I'll copy the stage and discharge data from the dialog and paste it into the spreadsheet. Also resulting from this tool, information needed is the gauge datum elevation. This is an NAVD 88 in this case, and it's 840.52. And I'll input this elevation into the spreadsheet as well. Now that the rating curve information is input into the spreadsheet, we'll need to fill in the cross-section geometry assumptions. This data can be accessed and determined through GIS mostly. For channel top width, it'd be a good idea to cut a cross-section from the best available terrain data. If you're using LiDAR, this would be sufficient to measure the top width from. But if NED is the only available terrain source, then I would use the ortho imagery to measure the top width. So I'm going to cut a cross-section based off of LiDAR data. And I'm going to use the MMC 3D Analysis Tools add-in. With this plot, you can annotate the bank elevations, and I can also measure the top width. So this plot can be easily referenced in the worksheet. I'm going to take a screen cap of it and paste it in. Then I can come back and reference this plot in the future. I'm also going to copy the station elevation data of this line and paste it into the spreadsheet. So it'll be used as a comparison with the calibrated cross-section geometry. So since it's based off of LiDAR, I'm not going to insert it into the area that references 10 meter DEM. There's actually a place to paste in station elevation data that was cut from LiDAR data. So input that, looks good. The range of elevation should update once you compute cross-section geometry through calibrating. So from that plot that I had, I actually measured across, and I know that this is the top of the bank elevation. It's actually shown in the leftover bank. And my measure across is about 460 feet. So I'm going to input that for channel top width. And you can see that once I enter that information, it automatically populates this value down here. Next is the channel end value. I'm going to start with an end value of 0.032. This is the Susquehanna River, so it should be pretty low. Next value is the energy slope. There's a couple different ways that you can get this data. If you have a model developed, you can use that. You can calculate the slope by using the add-in as well. I'm going to go with an energy slope around 0.0065. Invert elevation. This case I'm going to use the gauge datum elevation. I don't know what the actual invert is, if this is the right elevation or not, so let's go with the gauge datum elevation, which was entered down here. And then the next set of data I need is the bankful elevation. So we can go back to this plot, and I had annotated this vertex here, which represents the bank, which is around 852. After this information is filled out, the next step is to build the cross-section geometry. So we're going to do this by interpolating the top widths at each stage. The top width at the invert elevation will always be 0. So next is I want to define the bottom width of my cross-section. So I'm going to input an approximate bottom width, and we'll go with about 300 for now. Click on this cell and then use the Interpolate Top Width button to redistribute the top width at all stages based on its change in flow. So once I do this, it interpolates between 300 and 460, which is the channel top width I specified, and weights it based off of the flow that's calculated. Once that occurs, cross-section geometry is computed, and you can see it's plotted here in red. It also shows my LiDAR cross-section plot. If I want to adjust these so that they line up horizontally better, then I can put in an offset value. So I'll go with 50, which looks pretty good. I could probably move it over some more. So we'll go with 80. That lines up pretty well. Over here in this left plot, in black is the USGS rating curve data that we extracted from the tool, and in red is the computed. So you can see it doesn't line up the greatest, so in that case I'm going to go in here and change some of the parameters. I would start with the n value. I can probably increase that a little bit, and maybe even increase my energy slope if I would have done some other calculations in GIS to determine what that was. One other thing I'm going to change is actually my bottom width. You can see from the LiDAR that it's at least this wide at this point. So let's increase that to 340. And now I need to reinterpolate these widths. So you can see that lines up pretty well now. This point up here is almost exactly as the USGS rating curve data has it. Maybe I can increase that a little bit more. Reinterpolate. Now I'm a little higher than the rating curve. So that looks pretty good. So go ahead and save that. If I wanted to tweak these values and make this rating curve fit even better, I would adjust the n values. So let's see, I can move some of these over a little bit. 0.038. You can see it's starting to line up a little bit better, the bottom half of the curve. But just keep in mind that if you do change these, sure, your rating curve may match better, but it's not changing the geometry at all. Once the parameters are adjusted and you're satisfied with your results, you can enter a known elevation that you want to interpolate discharge and flow area at. This information would be used for the Create Channel Bathymetry tin with cross-section template tool in the MMC Bathymetry toolbox if run using the Compute Normal Depth or Flow Area templates. So in this case, if I wanted to calculate discharge or flow area below a certain point, say 846, because that's the lowest point of my LiDAR. And I would enter that, and it automatically interpolates those values based off of your rating curve information.